Good morning, all of you. Yes. So coming to the next numerical on flat plate collector or the liquid flat plate collector. Here it is given that a flat plate solar water heater. So whenever this solar flat plate water heater is given, one has to recall this liquid flat plate collector geometry and other details. Then in that they have given the number of tubes. That is 12 copper tubes are there. So whenever copper tube is given, the surface absorber plate is also made up of copper. Okay, each of 2.5 centimeter outer diameter. So many numericals we consider this outer diameter itself is a diameter or inner as well as outer diameter, imagining the negligible thickness. So that diameter is given 2.5 centimeter of the tube, and it is soldered to the underside of the absorber plate made of copper. So again, copper is for the absorber plate also. Underside of this copper plate, these tubes are welded or soldered, or it may be connected with bond. So here they have given soldered. It is soldered to the underside of the copper plate. So 12 tubes are connected like this, and now the absorber plate is ready to absorb the heat. And tubes will heat or transfer the heat to the liquid, and the liquid is water. So means we need to recall the properties of water also. The collector is 3 meter by 3 meter in size. So length of the collector surface is 3 meter, width is also 3 meters. So it is a square type of flat plate collector, and its average surface temperature is, so here collector temperature is 80 degrees centigrade. Collector temperature is given. The water flows in the tube with 1.2 meters per minute velocity. So water is flowing with a given velocity. So why these other details are given, we'll see later. Water flows in the tube in with velocity of 1.2 meter per minute at 60 degrees centigrade. So water is flowing at the inlet side or in the tube at this temperature 60 degrees centigrade. Find the exit temperature of the water. So question is here, to find the exit temperature of the water means you have to recall all the heat transfer equations to find this exit temperature of the liquid, which is flowing through this heat exchanger, or it is flowing through the uh, absorber tubes. Assume the transmissivity of the glass, that is tau. Tau value for the glass cover 0.9, and absorptivity for the absorber plate is 0.95. So these are the two values given for the glass cover, and absorptivity is given for the absorber. Neglect all other losses. So any other losses, like as I told, because of the bond or soldering, any resistance is there, that you can neglect, and also the losses from the top, sides, and bottom, that also they have told neglect. So we are not going to recall those equations. Finally, in the complete question, if you see, we need to find out only the exit temperature of water. So you have to get the details of water properties and the details of the tube or the absorber dimensions. So using these things, one can find out what is the exit temperature of the water. And also in the question itself, they have mentioned you can also use the properties of water. As I said, density of the water. So they have not given 1000. They have given 983.3. So for this density of water, the type of water, kg per meter cube, you have to use in this problem. Then viscosity of the given water is 4 point, or mu value is given 4.7 into 10 raised to minus 4 kg per meter second. So we'll see in the problem solution how these values or the units are useful in the given different formulas. So viscosity, density, Cp value, heat capacity of water at constant pressure, if you see. So all of you already know this value, 4.2 kilojoules per kg degree centigrade. Then this is Prandtl number, PR. So whenever this Prandtl number comes into picture, then we are going to talk about the non-dimensional numbers like Nusselt number, Reynolds number, or Grashof number. Okay, so using those all non-dimensional numbers as well as Prandtl numbers, we are going to find how much is the heat transfer ability, or at what speed the heat transfer is going to take place, whether it is a laminar, turbulent, or it is a natural or forced convection. So to find all these things, we need Prandtl number maybe in the problems. So we'll see that where these Prandtl numbers will be useful. So that number is 3.01 non-dimensional number. Then K value is given. Heat transfer coefficient with the conductivity, that is 0.65 watt per meter Kelvin. So using these all numbers or values, now the question is find the exit temperature of the water. So coming to the analysis of this flat plate collector with tubes which are soldered at the underside, they have told the inlet temperature of the water is 60. Exit temperature of the water we need to find out for a given length of the tube. Okay. Now coming to the dimensions, as I told, the length of the tube, if you want to find out the length of the tube, you can imagine the length of the collector itself. Okay, almost same. So you can consider the length of the tube as 3 meters. And all of you know that the heat carried away by the water, because once the heat carried away by the water, if you understand, by that equation one can find out the outlet temperature of the water also. So that heat carried away by the any liquid is given by mcp delta t. So this equation, if it is not covered because it is in the later chapters in the heat transfer subject, you can recall from the applied thermodynamics or the applied thermodynamics subjects where you have used that mcp delta t, mass of the liquid flowing, cp of the liquid, and delta t. Delta t is what? The temperature difference between inlet and outlet temperature. So using that equation, one can find out what is the heat carried away by water, and we can find out also the exit temperature of the or the outlet temperature of the water by that equation. Then using this Prandtl number, where we can go for using Prandtl number is this Prandtl number we need for Nusselt number. So to find the Nusselt number, we need hk by d value. So here it is given hd by k, hd by k for Nusselt number. And how we decide this used to Nusselt number is by the Reynolds number. So if you just understand this problem, now heat carried away by water. So in what speed the heat is carried away, whether it is a forced convection or a laminar heat flow. For that also we can use this Reynolds number first to decide whether it is laminar flow or a turbulent flow, or it is a natural process or a forced process. So in that case, Reynolds number will give us the clear picture. So as all of you know, this 2300 number decides whether the flow is a laminar or a forced or a turbulent flow. So in that situation, we are going to use this equation rho Vd by mu. So rho Vd by mu, as the equation itself suggests, whatever the values given in the problem, all the values can be substituted here. Rho is given density 983.3, say 983.3 kg per meter cube. See why I am going by this process itself, Reynolds number and Nusselt number, because in the problem they have mentioned Prandtl number, okay, and also they have mentioned this mu value, rho value. So if you just connect these values, one can understand just to find out Reynolds number, then we can go for finding other terms. So first we'll decide by Reynolds number whether the flow is laminar or turbulent. So D, as I told, the diameter of the tube may be inside or outside. So as inside is not mentioned or the thickness is not mentioned, I can consider the diameter given in the problem, 0.025 meters. Then velocity is given in meter per, what is that velocity? Meter per minute is given. So to convert that meters per second, I am taking 1.2 by 60. This 1.2 by 60. Then mu value is given. How much? 4.7 into 10 raised to minus 4 kg meter per meter second. So already it is in the given SI units. So I can substitute all these values and you can check the answer. So Reynolds number is coming below 2300, that is 1044. So the convection process or the flow of the fluid is taking place with the laminar condition. So once you come to know that it's a laminar condition, then we are using either Grashof number or the Nusselt number, Nusselt number, depending upon this Reynolds number. So if the Reynolds number is laminar, then I can go for Nusselt number, or if it is turbulent, I can go for Grashof number. So this will decide us. This will decide the roughness or the surface uh, smoothness of the given water tube. So inside the water tube, how much roughness it is there. Depending upon that, how much heat transfer coefficient or the convective heat transfer coefficient can be flowing. So this can be given in the problem itself, because for different type of correlations or different types of tubes or different types of uh, this designs, we have different types of Nusselt numbers, different correlations. There are n number of correlations. So in that one of the correlation, this will be given in the problem itself. Maybe in a IA test or the exams, whatever is there, to find this Nusselt number, this should be mentioned in the problem or data handbook should be provided. So better, I think this equation for the Nusselt number will be given in the problem itself. So using this Nusselt number, one can find out what is the unknown value of this heat transfer coefficient H. Okay, so this H value is not known in the problem, diameter is known, K is given. But when H and Nusselt number both are two unknowns are there in the one formula, what we'll do, we'll take some correlations which are apart from this heat transfer coefficient by convection. Other than that, I can go for this correlation 1.86 REPR, that is Reynolds number into Prandtl number, into D by L raised to 0.33. So using this correlation, one can find out what is this Nusselt number value. Once this Nusselt number value is known, then I can find out convective heat transfer coefficient. Okay, so Reynolds number we have found out. See, now the answer is clear. Why we found out this Reynolds number? Because in the correlation for Nusselt number, I can use this Reynolds number. Also, Prandtl number in the given in the question itself, 3.01. Both are non-dimensional, no need to convert. But this T by L should be in meters. Both should be in meters. So diameter is 0.025 meters. Length is 3 meters. 3 by 3 meters. So 3 meters length I will consider. Then I can find out this Nusselt number as 5.58 is the Nusselt number. Now, once this non-dimensional number Nusselt number is known, using this in the regular formula, okay, I can find out this unknown H value. So H value comes to be 145 watt per meter square degree centigrade. So all of you take 1 or 2 minutes and check these values. Is this answer is correct? So I'll repeat this procedure, how you found out this heat transfer coefficient by convection, because heat transfer is taking place between absorber plate or absorber tube and liquid. That's why, keeping that convection process in mind, I am finding this H value, which will be useful in the later stage to find out the exit temperature of the water. Okay, so coming to this H value, I can correlate either the convective heat transfer process equation directly, but there we don't know what is the heat carried away or heat transfer. Q value is not known. If you take H value into delta T into area, that is one difficulty. And delta T, for that also we don't know temperature. So that is a difficulty in going for a convective heat transfer direct formula. In place of that, as in the problem itself, they have mentioned some other values as well as Prandtl number, then I can think about some correlations. So by correlations, if you want to solve, then for a convective process or a heat flow process or a fluid flow process, I can go by Reynolds number. So using this Reynolds number, one can decide whether to use Nusselt number or other number. So as the flow is in laminar, so I'll not repeat this because already you have studied in the fluid mechanics, that is rho Vd by mu for Reynolds number and in different concepts. So once this value is less than 2300, like 1444, I can go for Nusselt number. The regular formula is Hd by K for a pipe flow. So in that condition, if two unknowns are there, many correlations will be given. So these correlations, once it is mentioned in the problem, they have given Prandtl number, means I can go for one of the correlations which relates diameter, length, Prandtl number and Reynolds number. So using this correlation, I can find out Nusselt number. Now resubstituting all this Nusselt number value, diameter of the pipe and conductivity. See here, 0.65 watt per meter Kelvin. These values are given. So substituting those values, I can find out this H. Convective heat transfer coefficient 145 watt per meter square degree centigrade. Okay, now we just found out H value. So using this H value or heat transfer by the water, if you know the Q value, I can find out temperature at the outlet or the exit temperature of water. One more process is balancing the heats. So heat gained by the water is equal to heat supplied by the tube. So we assume that neglecting the losses by this term, neglect all other losses, bottom side loss, top loss of the flat plate collector, and as I told you, resistance between the surfaces or the different materials. All these losses if you neglect, then heat transfer from the flat plate collector or the tubes is equal to heat gained by the water. Assuming there is no resistance, there is no losses from the heat gained by water as well as heat supplied by the tube. So if you neglect that, I can equate these two for our convenience. Now, as I told, heat gained by any liquid in a tube or any process, we are using this MCP delta T. So delta T, as I told, temperature difference of exit temperature to the inlet temperature. And here you can see mass flow rate of water, we don't know how much mass flow rate of water is going place. But here some other values are given to find out this mass flow rate. CP value of water is given in the problem. Even though CP value of water is not given in the problem, you all can remember this value 4.2 kilojoules per kg degree centigrade, because that is CP value of water is a standard value. Then delta T here, T naught is unknown, Ti is known, because inlet temperature of water that is given in the problem. Water flows in the tubes at temperature 60 degrees centigrade. So this only we are taking it as inlet flow. And after heating, because you can see why I'm taking this inlet temperature 60 degrees centigrade, because the average surface temperature of the absorber plate is 80 degrees centigrade. Means this absorber plate at higher temperature will transfer the heat to this low temperature liquid. Then this 60 degrees centigrade water is going to heat maybe up to 80 degrees centigrade after a long time, or between 80 to 60 degrees centigrade, not beyond 80 degrees centigrade. Okay. So now coming to this formula, heat gained by water, all of you know. Then other side, heat supplied by the tubes. Okay. So heat supplied by the tube, if you consider, I can take this convective heat transfer equation. As I said you here, H value is required for uh, going for the Q equal to that convective heat transfer equation, area into H value into delta T. So similarly here, area of the inside or outside tube, because we are assuming that the thickness of the tube is negligible. This inside wall of the tube, if you consider area, I can consider it as pi d. Pi d is the cross section or perimeter of the circle, into length will be cylinder. So cylindrical tube will be there. So pi dl can be used for area in inner surface of the cylinder. H is the convective heat transfer coefficient into delta T. So that delta T you can see here, T wall temperature is 80 given in the problem, higher temperature minus lower temperature. 80 is given for the plate temperature, as well as plate temperature is also equal to tube temperatures. That's why I can consider this T wall as 80 minus T wall average. Now this is a problem here. T wall average, if you go, I have to take inside temperature. Inside temperature in the tube, what is the average? Or sorry, not wall, it is water. So water average temperature, if you see, I have to consider inlet and outlet temperature average. Okay, so now we'll find out these, some of the parameters which is unknown here, like mass of water flow as well as temperature or the average temperature of the water. So average temperature of the water, I told you, inlet plus outlet temperature divided by 2 for the average. Mass flow rate of water. So all of you can recall here the continuity equation, or else the equation for the real flows. In that condition, we know that area into velocity into density will give us the mass flow rate of the water in any closed channel. And here area, if you see in the closed channel, this area is for the circular pipe cross section area, that is pi by 4 d square. So cross section area of the pipe, because here pipes are given. In the pipe the water is flowing. So area I have taken pi by 4 d square. Velocity of the water is also given in the problem. So take it as per the given units. Okay, what are the units we want in the formula? You have to convert and take it for velocity. Then density of the water. Density of the water is also mentioned here. So what are the values mentioned in the problem? Same thing we'll consider in the solution. So substituting all these values, one can find out the mass flow rate of the water in the pipe. So per second, 0.01 kg of water is flowing. Okay, that is nothing but 0.01 kg per second. So these values we are finding to substitute in the main equation. I'll substitute mass flow rate of water 0.01 kg per second. I'll substitute this T water average 60 plus T naught by 2. Like this, MW and this 60 plus T naught by 2. So once you substitute all these values and simplify both sides, and taking T naught on one side, we can find out T naught is 72 degrees. And whether this answer is correct or not, one can understand by these values. Inlet temperature is 60. Maximum temperature or the heat what the tubes can supply to the water is 80 degrees centigrade. So the water is heated in between 80 and 60. So the value will be around 72 degrees centigrade. So please check this answer also. T naught value 72 degrees, or you substitute this 72 in T naught and check whether the both side it is same values are coming. So cross check will be inlet temperature and absorber plate temperature. So in between that water temperature will be there, because absorber plate cannot heat water beyond its own temperature, 80 degrees centigrade. It cannot go beyond. And as the inlet temperature of water itself is 60, it cannot go below 60 also. So in between 80 and 60 means it will be, means one idea is that water is heated compared to inlet temperature, and it is not heated beyond the absorber plate temperature. That is one conclusion. The audio and video is clear, or any disturbance?
Yes, sir.
Okay. So in this problem, this is actually a practical problem. Even though some assumptions we have taken some constant values or given values in the problem which are not actually for the standard values, but one can understand how to find out this inlet and outlet temperature of the water other than heat transfer equations or using the correlations. So depending upon that, I have taken this problem. Okay, because earlier problems we are just finding the bottom loss, side losses, and top losses of the flat plate collector, but inside which how the heat transfer is going to take place. Okay, so in that context, I have taken this problem to explain you the laminar type or using this Nusselt number importance in the problems to find this H value. Okay, so once these values are taken, I can balance these two equations and find the outlet temperature. Okay, we'll take the next problem. So next problem you can consider it for homework. I'll give just an idea because this is again entirely like a heat transfer subject problem. So you can just recall that concepts and get the answer. Or can also, if you are not able to find the books from the library now in the lockdown time, you can also check in the online what is the procedure to be followed to find these solutions. Okay. So problem given here is in a flat plate collector, solar collector, because why they are telling in all the problems solar collector, because whenever the heat supplied on the glass cover, if it is required, depending upon the location and time, one can find out the solar insolation or the solar radiation falling on the glass cover in some of the problems. That's why they mention solar collector, because if it is other collector or heat exchanger, then heat supplied by some combustion process or the other chemical reaction process, that heat should be considered. So here heat considered is what? The heat received from the solar. That's why it is mentioned flat plate solar collector. The glass cover upper surface temperature is 60 degrees centigrade. So glass cover upper side. This temperature of the glass cover, top glass cover, is 60 degrees centigrade, and the absorber plate surface temperature is 100 degrees centigrade. This absorber plate. Okay, so here absorber plate they are not shown pipes. We'll see what is the condition given here. Absorber plate temperature is 100 degrees centigrade. It is metal only, but which metal we don't know. Whether copper, aluminum, okay, or iron, we don't know. 100 degrees centigrade. The convective and radiative heat transfer coefficients from the absorber surface are here. Convective heat transfer coefficient is 3.6 watt per meter square Kelvin, which is convective heat transfer coefficient. Another is radiative heat transfer coefficient, that is 1.2 watt per meter square Kelvin, which is the radiative heat transfer coefficient. So these two values are given, HC and HR. HC, I'll tell you, we'll consider convective heat transfer coefficient. HR is nothing but radiative heat transfer coefficient from the surface. The convective and radiative heat transfer coefficients from the glass cover surface to the atmospheric air are, see, for the absorber plate also they have considered radiation and convection. For glass cover, from the glass cover to the outside atmosphere, the radiation and convection process will be there. And from the glass, what is the convective heat transfer coefficient? That is 24.5 watt per meter square Kelvin, and radiative heat transfer coefficient from the glass is 4.35 watt per meter square Kelvin. Okay, so for both absorber plate and glass cover, they have given the heat transfer coefficients by convection and radiation. Atmospheric air temperature is 30 degrees centigrade. So T ambient or the outside temperature is 30 degrees centigrade, and the absorber plate temperature is 100 degrees centigrade. Glass cover, the single glass cover temperature is 60 degrees centigrade. The glass plate thickness is 5 mm and its conductivity is 1.05 watt per meter square Kelvin. So thickness of the glass cover is given, then conductivity value K is given, that is around 1.05 watt per meter square Kelvin. So after taking all these given values, now what to do with this problem? We need to find out the heat loss from the absorber plate to the atmospheric air, okay, per meter square surface area per hour. Means what? They have not given area of the collector or the absorber plate itself. Nothing is given. But unit suggests that, see here, heat transfer coefficient or radiative heat transfer coefficient, unit suggests that it is all for per meter square. So similarly, the question also they're asking per meter square area and per hour, we need to find out what is the heat loss from the absorber plate to the atmospheric air. Okay, so considering both the conditions, glass as well as absorber plate, how much heat is lost to the atmospheric conditions. Okay, So from the heat transfer subject, you can also recall this circuit diagram, how to draw this in the form of a circuit. So here they have taken the absorber plate temperature Tp, okay, and in between Tp and glass cover, okay, what is taking place? One is radiation process, one is convection process. Both the processes are taking place, and between this plate and the absorber plate, there is what is kept there? Glass cover is there as well as air is there. Here they have shown, because actual vacuum cannot be maintained between the glass cover and the plate. So here air is present. So heat convected by air is also should be considered, because both are not in contact. Both are connected between air. So only radiation is not possible. Convection is also possible. So both processes are taking place because of the air. So that is resistance by convection or convection they have written. And after that, glass cover to atmosphere. How the heat transfer is going to take place? It is going to take place by radiation as well as convection. Then it is reaching to the ambient temperature or to the atmosphere. Okay. So these all processes I'll not explain. How to write this 1 by Hc, 1 by Hr. So you can recall from the heat transfer subject and take these all values as per this circuit diagram, and you can just take it all the heat losses sum of all the heat losses. So whenever area comes, you can take 1 meter square. Okay, and the values should be written in the answer as per hour. So just analyze this problem using the heat transfer subject. Later, if any doubts are there, we'll discuss in the other classes. So I hope all of you understood these problems on the flat plate liquid collectors, flat plate collector geometry, or problems on the transmissivity, absorptivity, and we also discussed the problems on finding the heat transfer or outlet temperature of the water or inlet temperature of the water. Same problem can be changed with the different values just to change the problem. And also we found that the flat plate collector can be considered as a pin fin, and using this efficiency or the effectiveness of the pin fin, we can also analyze the performance of the flat plate collector. Okay. So if this last question is understood, so just analyze this problem by heat transfer relations, and finally you find out the loss coefficients, heat loss coefficients from the plate to the atmosphere. That's all. Okay, you just consider convection and radiation process and find, because from the side or bottom if you want to find out, because question comes, sir, until now you told that only not only top losses, side losses and bottom losses will be there from the flat plate collector, but in this problem why not we are finding for the side and bottom? Because the problem itself they're asking find out the heat loss from the absorber plate to the atmosphere. So to the atmosphere means only top surface they're asking. So in that case, I am just talking about radiation and convective heat transfer losses at the top side. So once you find out that heat loss, take the sum of heat losses, and finally you can write the answer in the total heat loss is so much per meter square and per hour. Okay. So after this, we'll just revise this parameters affecting. This is a very important topic, theoretical part. That's the last part of this liquid flat plate collector unit. So coming to that parameters, I'll just glance these all parameters affecting the performance of flat plate collector or the liquid flat plate collector. So there are n number of parameters. So in the syllabus, I'm going to consider only these 8 main parameters which are going to affect the performance of the liquid flat plate collector. So first one is the selective coating. So this selective coating is done on the surface of the absorber plate to improve its absorptivity and the transmissivity. Of course, the absorptivity of these metal plates will be very high, and transmissivity value compared to glass covers, the absorber plate transmissivity will be very less because it's not transferring light, but some value will be there. Then another parameter is number of covers. So as you go on increasing the number of glass covers or the plastic covers, the efficiency or the effectiveness of this collector will also decrease. That we are going to discuss. Third is spacing between the covers. So between the covers, in the sense you are using more than one covers, like two covers or three covers or four covers. In that case, what the standard spacing should be maintained so that losses will be less. Heat losses from the absorber plate to the atmosphere should be less. That is one thing. Then tilt of the collector. It's nothing but the slope. How much slope should be maintained so that the heat losses or the heat collection by the absorber plate should be high throughout the day. Next is the incident radiation. So all of you know this incident radiation should be high. So as the incidence radiation is very high on the surface, the efficiency of the flat plate collector can be improved. Then inlet fluid temperature. So inlet fluid temperature, if it is maintained very low compared to the absorber plate, then of course the performance or the heat transfer will be very high between the tubes and the inlet fluid temperature. Next is the dust collection on the cover plate. So dust collection, what it will do, it will reduce the transmissivity from the glass cover, as well as the convective and radiative heat transfers will be reduced from the absorber plate, but the heat transmission from the glass covers will be reduced. So that is we are going to discuss. Then last parameter is the cover transmissivity. So cover transmissivity should be high, as well as the selective surfaces on the absorber plate, or the absorber plate should absorb maximum heat. So coming to the first part, selective coating, you can see here. Here in a table, we can just observe for a selective absorber. Here two selective absorbers are taken with 0.95, 0.12. So as the values indicates 0.95, I can assume this is a copper. Why? Because in the just now problem we have seen absorptivity of the given copper plate is 0.95, or in this also you can see the copper absorptivity, or nickel black you can see absorptivity is 0.868 to 0.97, which is quoted on the iron. So copper or iron will be very high absorptivity. You can assume this value for either copper or the iron. So many selective surfaces have been invented nowadays. So two absorptivity collectors, if you compare with non-selective absorber plate, means without coating the absorber plate with this high absorptivity or low emission coatings, in that case, what is the efficiency or the performance parameters of this collector? So in that, if you see non-selective surface, if it is there without any coating, if the plate temperature is 356 Kelvin, heat loss will be 3.87. See here, maximum of all the values, other selective coatings values. Then heat transferred. Here it is only 593 watt, but in the selective coating, if you see, it is 682 and 616. Okay, for the same given area. Then outlet fluid temperature, if you see, without any selective coating, it is very less, 341. But with the absorber coatings, you can see the outlet temperature is very high, 342, 342 point something, like that. Then efficiency values. So of course, if the absorber plate is having maximum absorptivity, then it is going to have maximum efficiency because it is giving more heat transfer and more uh, heat absorption in the absorber plate and the water tubes. And one of the benefit of this going for absorber plate selective coating is these selective coatings will have absorption, more absorption for less wavelengths or smaller wavelengths, and also they have very less emissivity for higher wavelengths, because emissivity in the sense it is a heat loss. Heat is transferred from the absorber plate to the atmosphere by radiation, so that emissive property or the emissive value should be very less. So that is possible when the wavelengths are very high in the infrared range. If the wavelengths are in visible or ultraviolet range, means they are incident on the absorber plate, that wavelength will be very less. So at very less wavelength, it should absorb more heat. At very high wavelengths, it should lose very less heat. So that is the concept behind for making these selective coatings. So these are some commercially available selective coatings. The thickness you can see here, less than 1 micrometer should be maintained because the heat transfer should be important for our absorbing tubes, not for the surface of the absorber plate. So thickness should be maintained very less. So these are some of the absorber plates with some properties, emissivity and absorption, so that you can go by PPT. Then very good selective coating can see nickel black or galvanized iron. On that you can going for this absorber coating with high absorption. Also black chrome on steel you can see 0.87 absorptivity or up to 0.93 also possible. Then emissivity is 0.09. So like this you can just find out online which are the other commercially available selective coatings or newly invented selective coatings. Then number of covers you can see here. So just I'll go by these values so one can understand. So in this table, if you see, the maximum efficiency is obtained, okay, with the maximum transmissivity absorptivity product. So this transmissivity is very important here. If the transmissivity is very high for the given cover, then the automatically the efficiency will be very high. Similar way, if the number of covers are very less, if without cover is used, the efficiency will be high. But what will happen? The loss of energy from the absorber plate will be high. So to reduce that, we are going for the number of covers. Also, it will overcome the dust collection on the absorber plate. So dust collection will be taking place only on the glass plate or the cover plate. Any dust falling on the absorber plate will reduce the performance. So in that case, at least we have to go for 1 or 2 glass covers, not more than that. If you go for 3, 4, 5, 6, the efficiency or the performance of the flat plate collector will go on reducing. Okay. So in maximum case, they go for 1, and in other case, they go for 2 also. So 2 glass covers are used just to have some vacuum in between 2 plates so that radiation or convective losses can be reduced from the entire collector. So that is one thing. Next is, here you can see without any selective surface. See here, without any coating if you go, even though by that 2 glass covers can be used when the surface is completely copper or aluminum or steel or iron, without any coating if it is there. As I told, for 2 covers, by maintaining these 2 covers, what will happen? The losses from the absorber plate can be reduced so that inside collector temperature can be maintained high. So that efficiency will be high with number of glass covers. So you can see here 2 or 3, the efficiency will be high. Then 4, 5, 6, if you see, the efficiency will go on reducing. But with selective surface, if you see, I can reduce the cost of these glass covers. I can go for only one, and I can uh, stop the using of number of covers. So that will reduce the cost also. So these two tables are with selective surface and non-selective surface. Now next part is spacing between the covers. See here. Now spacing between the covers and shading, if you see, it should be having very low shading. So that's why we need to go for tilt factor or the slope of the given surface, and shading should be taken care. So more shading should not happen. And this convective heat transfer coefficient for the loss, if you see, the more losses will be there when the spacing between 2 covers is between 2 to I think 3.5 somewhere here. If it is between these values, the heat transfer coefficient is very high for the losses if you see. So to reduce that loss, I can go for 3.5 or 4 from that value to maximum value. Means what will happen? Because of the more spacing between the glass covers, I can maintain maximum heat storage in the collector. Okay. So these two are the different curves for different temperature differences. So one example of flat plate collector with delta T, if you see 10 degrees centigrade, the heat transfer losses will be less. If the temperature difference is very high for different collector, then losses are also high. So like this, you have to observe what minimum spacing should be maintained between number of glass covers. So optimum is 4 to 8 centimeter you can maintain this 4 to 8, so that heat transfer coefficient by convection will be very less, and also losses will be very less. Okay. So tilt factor, as I told, here tilt factor, relative annual insolation. So insolation here they have considered on the left side percentage values. Say for example 1 to 0 or 0 to 100% solar flux which is falling on the collector. On the x-axis they have taken latitude, latitude of the location phi, or you can consider this beta value itself. Okay, if the beta and this latitude angle, if both are almost the same, then the solar insolation or the solar flux what is falling on the collector will be maximum. Okay, so keeping this in mind, if you see the beta value or the phi value, if the phi value is 30 degree or between this 10 or 15% from the phi value, then one can get maximum solar radiation falling on the absorber plate. Okay, with this tilt. So 30 degree into 0.9 or 1 if you take, almost both are same. So up to say 15% means maybe 1.25. Up to here, if you see two curves with tilt factor 30 degrees or nearby 30 degrees, I can get maximum solar flux which is absorbed by the absorber plate. But if you go beyond that or go on reducing this phi value or beta value up to 0, if you see this slope is 0 means horizontal, the absorber plate cannot absorb maximum energy from the solar radiation. So that's why this beta value should be near to 30 with 10 or 15% changes. Okay. So theory part you can read from the books. Again, this same parameters they have explained in that solar energy books. That also you can refer for theory part. Next is the incident radiation. So for that I have taken here solar flux graph. So this graphical representation will make us easy to understand the concepts. So here you can see in this graph, solar flux is shown on the y-axis. So as the solar flux goes on increasing from sunrise to up to afternoon, you can see the efficiency. As the solar radiation increases, efficiency also increases, provided this flat plate collector should be focusing towards the sun with tracking mechanism or else with some sloping system. So then only this incident radiation can be improved, because here sun radiation we cannot change. Sun radiation is fixed, but at what rate or what maximum solar radiations we can receive, that is by this process, by making the slope for the flat plate collector or giving some tracking mechanism so that entire day it will track the solar radiations focusing towards the sun. Or question may come here, this flat plate collector any design can be changed. Yes, if you go by reflectors, if you take large area for the collector and small area for the absorber plate, that can be improved. Or else you can go by some reflectors. Many reflectors can be kept on the ground to reflect on the sloped or flat plate collector with a slope. Okay, if you reflect all those energies, then automatically this flat plate collector or non-concentrating becomes a concentrating heat collector. That can also be done to improve this incident radiation. Okay, so that I will show you here how the flat plate collector can be converted into a concentrating type. Here, here, simple flat plate collector is kept with or without slope, and then here you can see number of glass covers or glass reflectors. Sorry, not covers. Glass reflectors are kept on all the four sides, or if it is sloped one flat plate collector, you can keep these glass reflectors as a mirrors on the ground also, or at different buildings you can locate, and those reflected radiations can be absorbed by the absorber plate. So by this we can increase the temperature of the absorber plate or the performance of the flat plate collector. Okay, so this is about the incident radiation, how to improve by our side. Next is the inlet fluid temperature. So whenever you maintain maximum delta T or the difference in temperature, the heat transfer process is very high. So similar way, on the y-axis you can see the fluid inlet temperature, lower to higher temperature. You can remember like that, lower to higher temperature. On the y-axis, if you see the performance or the efficiency of the flat plate collector. So whenever you go for higher temperature itself at the inlet of the heat exchanger or the flat plate collector, if I go for higher temperature, then the efficiency or the heat transfer process will be very less, because the absorber plate, which is itself is 100 degrees centigrade, you can assume if it's 100 degrees centigrade, there is no meaning of going for this inlet temperature of 100 degrees centigrade and heating the water for 100 degrees centigrade. No heat transfer required like that. But when you go for higher difference of temperature of liquid, say for example 40 is the liquid inlet temperature and 100 is the absorber plate temperature, then because of 60-degree difference, the heat transfer will be very high, efficiency is also very high. I hope you are getting. Efficiency is nothing but the actual heat absorbed by the liquid water in the tubes to the total solar radiation or the total heat falling on that absorber plate. That will give us efficiency of that absorber plate or the flat plate collector. So that's why in all the flat plate collectors we have to try to keep this inlet temperature as minimum as possible and absorber plate as high as possible. Then only this performance will improve. So this dust collection, so we don't have any control. Control we can do by either keeping this flat plate collector at the top of the building, or even though some dust collection will be possible there. So keeping this flat plate collector in very low dust areas, that is one thing. Or else you can keep this absorber plate anywhere, keeping this correction factors, that's around 0.92 or 0.99 or 1% of losses due to this only dust. Okay, so using this 0.92 or 0.9 correction factors with this dust, then we can calculate the performance of the collector. So that will reduce the problem of the collector. Why? Because you can say the collector efficiency may be 80 degrees centigrade, this 80% or 50%, whatever. But because of this dust collection over the period, what will happen? The performance of the flat plate collector will reduce. So that on an average, you can keep 1 or 2% losses already present in the flat plate collector due to dust. Then you can go on calculating the different things. Also, the selection of these parameters depends on the different locations, because different locations have different dust or density of the dust also different. Then collector orientation may be different. Okay, if the collector is having more slope and vertical collectors, if you see, dust collection will be less. And also the cleaning frequency, transmissivity, and the season. So depending upon this, the correction factors are used to find the performance of flat plate collectors. Then last is the cover transmissivity. So always the cover transmissivity should be very high. Provided with that high transmissivity, this absorber plate should also absorb the maximum energy. So again, in that condition, you can see the absorber plate. Again, I have taken the table for the absorber plate selective surface, not for the glass covers. So in that case, if the transmissivity value of the glass cover is even though maintained very high, okay, almost 90% or 95% transmissivity, if the selective coating is not done on the absorber plate, same energy will be lost in the same fashion, because transmissivity will be very high. It will transmit all the energy to the atmosphere. So in that case, again, you have to focus on the selective surface of the absorber plate. If the absorber plate is having good selective surface or the coating, then you can go for higher efficiencies. Okay, and also this emission you can see emissivity with higher wavelengths and higher temperatures, that should be very less. Okay, so this is all about the parameters affecting. So this is the theory part. So this question can be asked for in IATES up to 6.5 marks or 10 marks, and in exam it can be asked for 12 to 14 or 16 marks. So this is a very important question. Parameters affecting the performance of flat plate collector. So I think time is up. Okay. I hope the topics are clear to you. Hello? Is there any break now? Or next class is continuous?
Break is there, sir.
Break is there. Okay. So go through this video lecture. I will share this recorded video lecture later. So still, if you have any doubts, you can send the messages in the group. So there I can answer, or else you can ask in the next class, in the online class. We can clear all these doubts. Okay. Thank you. So from next class, we'll start with the third chapter. That is solar air heaters. Or I think, oh, just a minute, we'll see the syllabus. Okay, next class we'll start with the third module. So third module, whatever is there, we'll start from that part. So I'll stop the class here.